The comparison test is one of many tests that we'll use to determine if a series converges or diverges. As the name suggests, we're going to take a series whose convergence is unknown and compare it to a series whose convergence we do know and draw conclusions from there. So here's how it works. We're going to take two series, really. A sub n is going to be the series that we are given. We're going to take the series we're given, and we know this other series B sub n, and the terms have to be positive. You can make some really goofy examples where if that's not upheld, you get some strange behavior. So let's suppose that B sub n is convergent. That means, remember, these are all positive terms. That means that the terms approach zero. Any convergent series will have the terms approaching zero, and they approach zero fast enough for it to be a finite sum. If A sub n is less than or equal to B sub n, that means that the A sub n values are kind of trapped below those of B sub n, so the partial sums will all be less than the partial sums of B sub n, and so overall the partial sums of A sub n will, or the series itself will converge. On the other hand, if B sub n is divergent and A sub n is greater than or equal to B sub n, then the partial sums of A sub n will be greater than or equal to the partial sums of B sub n, but the partial sums of B sub n go off to infinity. And if we have a number that's greater than something that's going off to infinity, it will go off to infinity as well. So A sub n will be divergent. And here's how we do this. Find a sequence, B sub n, that's similar to the one that you've been given. We're trying to determine if A sub n converges or diverges. We want to choose a sequence of terms so that we know whether or not B sub n converges or diverges. We don't want to choose one where we don't know if it converges or diverges. If the series converges, you want to show that A sub n is less than or equal to B sub n, so that the partial sums are always less than those. After that, you conclude that A sub n converges. If B sub n diverges, show that A sub n is always greater than or equal to B sub n, if you can. And then you conclude that A sub n diverges because the partial sums of A sub n will be greater than or equal to the partial sums of B sub n. There are some series where we have to do some real mathematical gymnastics in order to show things like A sub n being less than or equal to B sub n, or A sub n being greater than or equal to B sub n. And we have another thing that's called the limit comparison test that we'll talk about in a little bit, which might save us from those things. Okay, one of the key things that we'll use from this is the p-series test. The p-series test says if you give me a positive power p and look at the series 1 over n to the power p, it will converge exactly when p is greater than 1. If p equals 1, we have the harmonic series, which we know diverges. That means the terms, although they do go to 0, they don't go to 0 fast enough. And if p is less than 1, it's going to diverge as well. So in the converging ones, converges, the series 1 over n to the 14th would converge. The series 1 over the square root of n cubed would converge because that's n to the 3/2. And we can even throw a constant up top like 18 over n to the 6th. That will converge because all of those exponents are going to be greater than 1. On the other hand, the ones that would diverge, we'll write this in red, the ones that diverge would be things like 1 over n to the 1/4 power, because 1/4 is less than 1. How about the series 1 over the cube root of n squared? That would diverge because that exponent is 2/3, which is less than 1. Or if I do the series 18 over n to the 0.6, that would diverge because that exponent is less than 1. These will come in handy quite a bit as we do this. We've got an example with several different series that we're going to determine whether or not they converge. Some of them may require the newly learned comparison test. Some may require some other things like the divergence test or the integral test. So for our first one, we've got the square root of n over n squared plus 1. I always look to make sure that the terms go to 0. If they don't, the series cannot converge. So in this case, the n squared has a higher power than the square root of n. As n goes to infinity, those terms will go to 0. Okay, so I don't think I want to use that. Well, I can't use that. So what I'm going to do is I'm going to compare the square root of n over n squared plus 1 to something that I can determine whether or not it converges or diverges. What I like to do is eliminate terms that, when n is really large, have no or very little influence on the whole thing. So in the numerator, of course, the square root of n is just the square root of n. But in the long run, that plus 1 in the denominator is insignificant compared to the n squared plus 1. So that's like n squared. Now these aren't equal, but for large values of n, they behave similarly. Now this guy, well, that's n to the 1/2 divided by n squared. And when I subtract 2 minus 1/2, I end up with 1 over n to the 3/2. So what I'm going to do is I'm going to compare my series to 1 over n to the 3/2, that series. Okay. Now I'm going to make some observations. I should also note that the terms are positive. All of the terms, I'm just going to go ahead and say this out front, all of the terms in the series that we're dealing with have positive terms. So we don't really need to worry about that too much. Okay, so I know, let's compare the square root of n over n squared plus 1. And think about what happens when I drop off that plus 1, n squared. Think about the denominator. The denominator had a plus 1, now it doesn't. So that means the new denominator is smaller than the old denominator. The new denominator is smaller than the old denominator. If you make a denominator smaller, the resulting fraction will be bigger. Let me argue that again. I have the n squared plus 1. I drop off the plus 1. I get a smaller quantity in the denominator. When a denominator has a smaller value than another denominator, but the numerators are the same, the resulting fraction will be bigger. Think about starting at 1/3, making that denominator one smaller at 1/2. I'd rather have half a pizza than a third of a pizza. Okay, so I've made this observation, and the sum 1 over n to the 3/2, well, we got to think about the comparison test. My terms are smaller than these terms, which is a good thing, because the partial sums for my series will be smaller than the partial sums for the series that I'm given, and the series that I'm given converges by the p-series test with p equal to 3/2, which, by the way, is greater than 1. We need to kind of acknowledge that. So, my series will converge by the comparison test. That's basically the general argument. So let's walk through that argument again. I found a series that was larger than my series. The series that I found converged. However we show it converges, it's okay, but it converged by the p-series test. Because my series had smaller terms than the convergent series, my series will also converge using the comparison test. Okay, let's look at our next example. This actually was used in the integration or the integral test video. If you want to look back, we looked at this. We actually know from that particular video that it does converge, but we'll use the comparison test for this one. Okay, so using the comparison test, what I'm going to do is, once again, I'm going to think about 4n over n to the 4th plus 1. Okay, well, for large values of n, things that are smaller in power are insignificant. So I have n to the 4th plus 1. The plus 1 is insignificant compared to the n to the 4th. And this reduces to 4 over n cubed. Okay, now I know that the series of 4 over n cubed will converge by the p-series test. P is equal to 3 this time. The 4, again, we can just kind of pull out. That converges. And so my series probably converges, but I've got to make sure that I get the right inequality. Okay, so let's look at this. 4n over n to the 4th plus 1. Let's compare that to 4n over n to the 4th. Why? Because that's what we used to come up with the 4 over n cubed. This is very similar argument. We have the plus 1 here. We drop that off. Our resulting denominator is smaller. When the resulting denominator is smaller, the resulting fraction is larger. And the series of 4n over n to the 4th, oh, well, we can simplify that, of 4 over n cubed converges by the p-series test with p equal to 3, which is greater than 1. So our series will converge by the comparison test. Again, think about what this means. The partial sums for my given series will be less than the partial sums for the series at hand, 4 over n cubed. Since this converges, I don't know to what, but it converges to something. That means that since the partial sums are less than the partial sums, that our series will converge as well. All right, same business. Let's try this out. I've got the square root of n over 2n minus 1. The numerator is approaching infinity. The denominator is approaching infinity. I didn't do this in part B, but here I'm going to do this. Do the terms go to 0? Yeah, they go to 0 because the denominator has a higher power than the numerator. Okay, so let's see here. I'm going to think the square root of n over 2n minus 1. For large values of n, we can ignore the minus 1. So that's like 2, or square root of n over 2n, which is n to the 1/2 divided by 2n. And if you subtract 1/2, or 1 minus 1/2, we end up with 2n to the 1/2 under 1 there. Now I want to think about this series. I don't really need the 2 there, so I can pull that out front. But I've got 1 over n to the 1/2. Does it converge or diverge? Oh, this is another p series. This time p is equal to 1/2, and 1/2, when p is 1/2, it diverges because that's less than 1. Okay, so I suspect it diverges. Let's go for it. So this is the start of my argument. The square root of n over 2n minus 1, we're going to compare that to square root of n over 2n over 2m. What have we done? We removed the minus. We removed a deficit. So our new fraction with 2n is larger than the old fraction. If your denominator gets bigger, your fraction gets smaller. The resulting denominator is larger than the original denominator. If the new denominator is larger, the whole fraction is smaller. So this is going to be like so. Now I'm going to make this little observation. We've already gone through this. That's the same as 1 over 2n to the 1/3. And the sum of 1 over 2n to the 1/3 diverges by the p-series test with p equal to 1/2, which is less than 1. So our series will diverge by the comparison test. Again, my partial sums are bigger than the partial sums of this series that I know diverges. In order for this series to, or because this series diverges, that means it goes to infinity. And since our partial sums are bigger than the partial sums here, they'll also go to infinity. Okay, so let's look at the next one. We've got 2 to the nth minus 1 over 4 to the nth plus 1. Now, this is slightly different because it's not a rational function. It's not rational because the numerator and denominator are not polynomials. But we do have this idea that the numerator, 2 to the n minus 1, will go to infinity, as will the denominator. So this will be an infinity over infinity indeterminate form. So I can compare this to something where I drop off the insignificant terms. We've got 2 to the nth minus 1 over 4 to the nth plus 1. I'm going to do this in 2 steps. First of all, let's do the denominator because that's what we've been playing with. I'm going to remove the plus 1 in the denominator. If I do that, my new denominator is smaller than the old denominator. If your denominator gets smaller, the fraction gets bigger. Now, on the other hand, if I replace the 2 to the n minus 1 with just 2 to the n, the numerator went from 2 to the n minus 1 to 2 to the n. We left off the minus 1, so the numerator got bigger. If the numerator gets bigger, the whole fraction gets bigger. So we have the same inequality all the way along. Now this simplifies to 2/4 to the nth, which is just 1/2 to the nth. Okay? Now let's think about the series of 1/2 to the nth. The series of 1/2 to the nth. Well, this is different. This isn't a p-series problem anymore. Okay? A p-series has to be 1 over n to a power. That's not like this. Here, instead, we have a constant raised to the nth power. So this is a geometric series. When you have terms where you have a constant raised to a power, you have a geometric series. The common ratio is 1/2. What is it that we're raising to the nth power? We're raising 1/2 to the nth power, and that is less than 1 in absolute value. When the common ratio was less than 1, the series converges. So I'm actually making that statement a little bit early. Because this series converges, I suspect my series converges. Now I'm going to write the rest of my argument. My argument kind of starts there. But now it's really sounding like our argument. So 2 to the nth minus 1 over 4 to the nth plus 1 is less than 2 to the nth over 4 to the nth. I'm skipping a little bit of that inequality, which is equal to 1/2 to the nth. Because my partial sums will be smaller than the partial sums with 1/2 to the nth, and 1/2 to the nth converges, that series converges. So the series 2 to the nth minus 1 over 4 to the nth plus 1 converges by the comparison test. Very cool. So there are lots of different flavors that these can take on. Now, I do want to make one comment. The p-series test and the geometric series might mess you up, and I'm going to explain why. Here, p was equal to 1/2, which was less than 1. When the power is less than 1 in the p-series test, it diverges. Well, here, the common ratio was 1/2, which was less than 1. And that guy converged. Okay, so the geometric series and the p-series test, we're always comparing to 1, whether we're geometric or p-series, but they flip-flop. The p-series diverges when we're less than 1. The geometric series converges when we're less than 1 in absolute value. So be careful about that. Okay, one more example here. I noticed that these terms definitely go to 0. The numerator is 1, the denominator is just n times something else, the natural log of n squared. And so how do I compare this to anything? I have no idea how I compare this to anything. Okay? It's kind of like 1 over n. 1 over n diverges, but I get a little boost from the natural log of n squared. Okay? I get a little boost from that. So is that enough of a boost to push it over from diverging, where 1 over n diverges, to converging when with that extra little factor? I don't know. Let's find out. The comparison test, I really don't have anything I can drop off here. So I don't think the comparison test is going to be very appropriate. What I'm going to use instead is I'm going to use the integral test. Integral test. Okay, for the integral test, we are going to let f of x be equal to 1 over x times the natural log of x squared. And there were 3 things that we had to identify before we could use the integral test. F is positive, is it? I don't know. Well, I've got the natural log of x and I'm squaring it, as long as the natural log of x is not 0, and it won't be. Natural log of 1 is 0, and we're not even including n equals 1. So I've got any number squared, it's going to be positive. X is already positive, so we're good. F is continuous. Is it? I don't know. The only way it wouldn't be continuous is if the denominator is 0. Well, the denominator will equal 0 if x is 0. Well, that's not in our range. And if x is 1, the natural log of x would be 0. That would be a problem. Well, that's not in our range. So that's okay. And decreasing, well, that's pretty clear that it's going to be decreasing because each time the denominator is getting bigger. Okay, the natural log is an increasing function, so is x, so it's going to be an increasing function. So we can use the integral test. So here we go. We want the limit as b approaches infinity. I'm just going to jump to the chase here. Of the integral from 2 to b, we want to start at 2 because that's where our sum starts, of 1 over x, natural log of x, quantity squared, dx. We need to think about how to integrate this. Way back in the integration techniques, I have suggested, if you watch those videos, I suggested whenever there's a natural log, think about the substitution rule first. Let's try that out. Well, if I do substitution, I suggested in those videos that you would let u be the natural log of x. Is the derivative of the natural log of x lurking about? Well, it is. It's right there, 1 over x. Okay, so substitution is appropriate this time. So we're going to let u be equal to the natural log of x. Du is 1 over x dx. So 1 over x dx will become du. Got the limit as b goes to infinity. Integral from x equals 2 to x equals b. 1 over x dx becomes du. And then the natural log of x is u. Okay, so that's going to be u squared in the denominator, which is the same as u to the negative 2. So let's find the antiderivative. Limit as b goes to infinity. Remember, that's u to the negative 2. So we would add 1 to the exponent. I would get u to the negative 1. We have to divide by negative 1, which is like multiplying by negative 1. And we're going to go from x equals 2 to x equals b. I keep saying x equals 2 to x equals b because my variable after substituting is now u. So we've got to resubstitute here. I'm going to resubstitute and rewrite it using the negative 1 exponent. So we'll have negative 1 over u, right? U to the negative 1 is 1 over u. U is the natural log of x. We want to evaluate this from 2 to b. So we've got the limit as b goes to infinity of negative 1 over the natural log of b minus a negative 1 over the natural log of 2. So here's the action. B is going to infinity. The natural log of b also goes to infinity. The natural log, that's in the denominator. If the denominator is going to infinity, then this is going to go to 0. the 1 over the natural log of b. So that's going to go to 0 plus 1 over the natural log of 2. It's 1 over the natural log of 2. Okay, so that means that our series, I'll write the conclusion over here, our series converges by the integral test. Different. Okay. Our final example deals with something called the limit comparison test. The limit comparison test is useful when you have something that kind of looks like it could be done by the comparison test, the ordinary comparison test, but the inequalities don't line up the right way. So the limit comparison test says we are given two series with positive terms. Again, we have to have positive terms. One of these series will be given to us, the other we're going to make up. Okay, just like with the comparison test. Okay, here's what we're doing. Notice there are no sums in what I'm about to write. If the limit as n goes to infinity of a sub n over b sub n is equal to c, some positive finite number, which is greater than 0, then either both series converge or both diverge. Okay, so how does this work? We're given a sub n. We choose b sub n. We choose b sub n so it looks kind of like a sub n. We also choose b sub n to be a series whose convergence is known. I know it converges or I know it diverges. Okay? Then we take the ratio of the terms, drop off the sums. We take the ratio of the terms, look at the limit as n goes to infinity of that. If it equals some number c, which is a positive value, they both converge or diverge. Okay? All right, so we want to use the limit comparison test to determine if this series converges or diverges. Okay, so I do the same thing that it did before. So I'm going to use the notation of our theorem. Let a sub n be equal to 4n over 2n to the fourth minus 1. And b sub n is going to be something that looks like that. Well, in the long run, when n is large, that minus 1 is insignificant. It's going to be 4n over, just let's do the 2n to the fourth. So it's very similar to what we did before. Now this reduces to 2 over n cubed. Okay? I'm going to look at the limit as n goes to infinity of the ratio of these two things. So the limit as n goes to infinity of a sub n over b sub n is the limit as n goes to infinity. Let's see here. A sub n is not very pretty. 4n over 2n to the fourth minus 1. B sub n is 2 over n cubed. I'm dividing a fraction. I didn't write that very big, so let me give myself a little bit more room. N is going to go to infinity. When you divide fractions, you take the reciprocal of the denominator and multiply by that reciprocal. So it's going to be n cubed over 2. Now we can reduce 4 divided by 2 is 2. And we end up with the limit as n goes to infinity of n to the fourth, that n to the fourth coming from the n and the n cubed. However, I did forget the 2 that was there. Divided by the denominator, which is 2n to the fourth minus 1. Okay. Now, in the long run, for very, very large values of n, 2n to the fourth over 2n to the fourth minus 1 is going to be 2n to the fourth over 2n to the fourth. Hey, look at that. That's equal to the limit as n goes to infinity of 1, which equals 1. Okay. We did this long problem. I have no idea why I did it. Now let's look back. Okay. Why did I take this limit of these ratios? I did it because I'm using the limit comparison test. So let's if the limit is equal to some number c, which is greater than 0. Hey, this is greater than 0. Then either both series converge or both series diverge. Okay? Now, I chose a sub n because that's what I was given. I made up B sub n because that would look similar to A sub n. And B sub n is a p-series with p equal to 3, which is greater than 1, so it converges. So let's write all that business out. The limit is 1, which is greater than 0, and the series of 2 over n cubed, I'm going to run out of room, converges by the p-series test, p equal to 3. So my series, 4n over 2n to the 4th minus 1, converges by the limit comparison test. Okay? Now, why is this helpful? It's helpful because this series, it can be done, but it takes a little bit of finesse. It's not easy to use the comparison test on that series. Like I said, it can be done, but it's a little bit sneaky to do. So the limit comparison test is kind of like a sledgehammer that smashes this thing out. So